Welcome to lecture 4 in this series on Riemann surfaces and algebraic curves. So what we will try to do in this lecture is to try to put Riemann surface structures on the cylinder and the torus. So let us begin with the cylinder. So let me write that down: Riemann surface structures on a cylinder. So you see, we visualize the cylinder in 3 space as follows. So these are the axes, and we have here the unit circle, which is usually denoted by S1, the one sphere, and then we have the cylinder with this as base and with axis parallel to the z axis. So this is your cylinder here, and let me call it as script C. You can see that this is just S1 cross R, where this S1 is the unit circle, and R is of course R refers to the z axis. Okay, so here is my cylinder, and basically I want to turn this into a Riemann surface. Okay, so what is our aim? Our aim is, given any point on the cylinder, I will have to produce a small disk like neighborhood and a coordinate chart on that neighborhood, which identifies it with a piece of the complex plane, in fact with a small disk like a disk on the complex plane, and then I will have to give you a collection of such charts which gives you an atlas. And of course then the Riemann surface structure that I am going to talk about is going to be the Riemann surface specified by the maximal atlas which contains that atlas. Okay, so well, so somehow I will have to connect this to the plane, and in this case it is very easy to do that in an intuitive way. So what I do is that, well, let's draw a dotted line on the cylinder parallel to the z axis, and assume that, let me just cut it up, cut along the dotted line, and when I do that, what I will get is basically I will get a strip like this. I will get a strip. Of course it is going to look like a vertical strip which is going to be which is going to go to infinity in both directions vertically, and of course this length is going to be the equal to the length of the unit circle. And well, how do I undo this operation? I undo this operation, well, by actually identifying the edges. So this strip has 2 edges, and I put arrows to tell you that you have to identify this edge with that edge, namely just you stick this edge to that edge and you will get back your cylinder, right. Well, so here is my here is my strip. It's still not quite the plane, but you can make this into the plane in the following way. What you do is, well, at least for the purposes of the present lecture, at least for the moment, let me erase this dividing line, because I may need the whole of this blackboard. So you see, what you do is you just, well, take this strip and repeat it infinitely, that is, put several infinitely many copies of this strip on both sides, and if you continue it you get the plane. Okay, so I'll do it like this. So what I do is, well, there is no particular way to do it, in the sense that I can think of the strip to be like this. So here is my strip, and let me call this as a copy 1 of the strip. Okay, I put another copy of it on this side. Here is copy 2, and then I put one more. Here is copy 3, and so on, and I do it also on in this direction. Okay, so I put one more copy here. If you want, I will call it copy 1 prime, and then yet another copy 2 prime, and so on. When I do this, what I get is really the complex plane. Okay, so you see here is my complex plane. See, and well, how do I go from back from here to here? To do that, all I have to do is, well, choose a point here on one of these lines that form the edge of one of the edges of the strip, call that as the origin, okay, and then draw the axis there, the usual axis like this. So this is the real axis, and this is the imaginary axis. Incidentally, you should not confuse that z with the z here, because this was the z in R3, and you should forget this z when I am talking about that. Okay, well, maybe I'll put a z like this so that you don't get confused with this z and that z. Well, and then I draw this perpendicular. And I take this vector. So this is a complex number z0. Okay, and you can see that translation by z0, the translation map by z0, which is take any complex number z and translate it by z0. So this is z plus z0. Translate it once more. I am going to get z plus 2 z0. Okay, and translate it, well, in the other direction. So this is z minus z0. Translate it once more. I will get well, z minus 2 z0, and so on. So this is the translation by z0. If I do it so many times, then you see that this translation by z0 will map this strip exactly onto this strip. Translation by 2 z0 will map this strip onto that. Okay, and translation by z0 by minus z0 will map this strip onto this. Translation by minus 2 z0 will map this strip onto this. So this translation by multiples, integer multiples of z0, is precisely the operation that identifies all these strips together to give you back the strip. Okay, so that is the whole point of trying to get a complex structure on this. So we will have to now formalize this. So what you do, we do the following thing. We take the complex plane, we define an equivalence relation. What you do is you fix a z0, a complex number z0, and make sure that z0 is not 0. Okay, so you think of z0 like this, and what you do is for z and z prime complex numbers, we define z is equivalent to z prime if and only if equivalent if and only if z is equal to z prime plus n times z0, where n is an integer. So this script z denotes the set of integers. Okay, okay, so you can easily check that this is an equivalence relation. Okay, and therefore you can look at the set of equivalence classes. Okay, so what you do is consider the set of equivalence classes which I will write as C mod tilde. So this is the usual notation, set modulo and equivalence relation, okay. And you also get a map C to from the complex plane to C mod tilde, and I will call this map as pi. This is a natural map which takes any complex number z to its equivalence class. This is the equivalence class of z under this equivalence relation, okay. So if you think about it, if I take z0 to be this vector here, this complex number here, then C mod tilde, the set of equivalence classes, is precisely my cylinder, because you see what is going to happen is that all the copies of the strip are going to get identified with one copy. So I am going to get this, but the identification is still not complete, because on this there are still, given a point here, it has to be still identified with the corresponding point here, and given a point here it has to still be identified with a point here, and that is because they are still translates by z0, okay. So I still have to do essentially gluing this edge with this edge. It is only then that I get this set of equivalence classes, okay. So I therefore get the cylinder, okay. So C mod tilde is just C at least as a set that is because it can also be seen in another way if it makes it more clearer for you. Take any point in C mod tilde, that is an equivalence class, okay. Now what I want you to understand is that if you take a strip like this, any point inside, okay, if you take its equivalence classes, it will be full of points which are translates of this point, and if this is an interior point of the strip, you will get exactly one point. So for all the interior points of a strip, they are the unique representatives for their equivalence classes in that strip, okay. So that is what happens to interior points, okay. But if there is a point on the strip which is a boundary point, then in one strip you get two representatives, namely the point on one edge and the corresponding point on the other edge. And so if you want to still get an equivalence, if you want to go do the equivalence, you still have to identify these two, and when you do that you get the cylinder, okay. So you must understand that this cylinder is exactly C mod tilde, at least as a set, okay. And that is the whole point. The point is that you are able to realize a cylinder as a set of equivalence classes for a nice equivalence relation on the set of complex numbers, and this is what will help you to give a Riemann surface structure on the cylinder. So let me make a couple of remarks. The first thing is, well, you see, notice that number one, if P is a point of the cylinder, okay, if P is a point of the cylinder and Z is a complex number with pi of Z equal to P, so you see I am identifying the set of equivalence classes at least as a set with the cylinder. So well, if you give me a point P on the cylinder, okay, now that point P is going to correspond to a point on the strip. Either it can correspond to a point in the interior, in which case you will get only one point, or it may correspond to 2 points. If it is a boundary point, I will get 2 points, so I will get P prime and P double prime, I will get 2 points, okay. And well, if I look at this point in these many copies that I have written down, then saying that the image of Z is P is the same as saying that that is one of those points. So Z is a point which goes to P, okay. The way I have drawn it, this Z has to go to this P because this is an interior point of the strip, so it has to actually go to this, but this Z could have well been on one of the edges, alright, and that is the situation I am looking at. I am taking a point of the cylinder, you think of it as an equivalence class and you take a representative of the equivalence class, okay. Well, take this, then what is pi inverse of P? Pi inverse of P, if you look at it, it is going to be just the equivalence class. The set of points equivalent to Z, right. So because what is this map? It takes every point to its equivalence class, and so if you take the inverse image of an equivalence class, you will get all the points in the equivalence class. That is exactly what you will get, right. So pi inverse of P will be the set of all those points that are equivalent to Z, and you can see that that is nothing but pi inverse of P will be just Z plus integer multiples of the point Z0, because the set of points equivalent to Z is all the translates by integer multiples of Z0, which is what I have drawn here. These are all the translates, okay. So the inverse image of a single point will be this set of points, they are all translates of Z, okay. So that is what you will get, and what this notation means is this is a set of all Ez plus n Z0 where n is an integer, and you can see that this is bijective to Z if you want. It is just a copy of Z, because I will have to just map this Z plus n Z0 to n, okay. So it is a copy of Z, you take any point, the inverse image is just a copy of Z, right. Well, I can generalize this a little bit more. If S is a subset of the cylinder, okay, and S prime is a subset of the complex plane such that pi of S prime is equal to S, and say pi restricted to S prime is bijective, okay. So here what I did was I took a point on the cylinder and I took a representative, okay. Here what I am doing is I am taking a subset of points on the cylinder and I am taking a subset of representatives, okay, and then the same kind of argument will tell you that pi inverse of S will be nothing but S prime plus all the translates of S prime, okay. So it will be S prime plus again Ez times Z0. This is going to be the set of all S prime plus n Z0 where S prime belongs to capital S prime and n belongs to Z. This is what I am going to get, okay. I am just trying to make you understand what this map is. I am just trying to make you understand what this map is, okay. So it is very clear that now if I choose on the strip a very small disk, if I choose a very small disk here, so the radius of the disk is extremely small, okay, then, and suppose I call this disk as say D, right, then if I take the image of this D in the cylinder, what I am going to get is I am going to get a small disk like neighborhood surrounding the point P, okay. So it is going to be just so what I will get here is, so well, let me rub the circles off and draw it like this. So here is my D. Okay. So if I take a disk like this and I take its image, I am still going to get a disk here, a disk like neighborhood, and if I take the inverse image of this, okay, what I am going to get is I am going to get all possible translates of this disk by integer multiples of z naught. So this is what I am going to get, okay. And since I have chosen the disk sufficiently small, the map pi, mind you, the map pi is, this is the map pi, this is exactly the map pi. What this map pi is going to do is it is going to map all these translates of z to the point P, and all these disks to this disk here, okay. So well, I can call, let me call this as pi d, I will call this as pi d, and I can use this to now give a coordinate at the point D, okay. And why is that? That is because of the fact that, well, I just now said that this cylinder is just the set of equivalence classes as a set, okay. It is just a set of equivalence classes as a set, but then the cylinder has more structure. In fact, it is a topological space, and it is a nice surface in R3, and you can do calculus on it if you want. There is a notion of differentiable functions and so on and so forth, whereas the set C mod tilde does not seem to have anything. So to begin with, at least you can put a topology on C mod tilde, on the set C mod tilde, so that the identification of C mod tilde with this cylinder is a real identification even as topological spaces. And the way you do that is a standard technique in topology, which is called giving the quotient topology. So let me come to that. Give C mod tilde, the set of equivalence classes, the quotient topology. What is this quotient topology? The quotient topology is a set here is open if and only if its inverse image under pi, the set given by the inverse image under pi, which is a subset of the complex plane, that is open, okay. So and a set in the complex plane, of course, you can recall, is said to be open if it is a union of disks, okay. So yes, a subset is said to be open if pi inverse of S is open in C. So this is called the quotient topology, and this is a technique that can be used whenever you have a surjective map from a topological space to any set, okay. If X is, whenever you have a topological space and you have surjective map to any set, then to this set you can give a topology by, namely the quotient topology, namely you call a subset of the target open if and only if the inverse image under this map is an open set in your source topological space. So that is what I am doing here. Now the advantage of this definition is that it automatically makes pi continuous, because, well, this is actually begging the question. You see, if normally if you are given two topological spaces and if I give you a map, when do we say that it is continuous? Only when the inverse image of an open set is open, but now I am demanding the inverse image of an open set to be open. So this automatically makes pi continuous, okay. So this automatically makes pi continuous, this automatically makes pi continuous, and in fact what it does is that it actually identifies the set of equivalence classes with the cylinder even topologically. Now the identification is not just as a set, but it is an identification also in the topological sense. That is because you see, if I now take a point z and if I take a disk, small disk d surrounding z, then its image here will be a small disk like neighbourhood pi d surrounding the point p, and if you now take this set, this is open because pi inverse of pi d is d, the union of d and its translates, okay, that is a union of open sets, so it is open, so that makes pi d open, okay. So what we have actually proved is that pi is an open map, that is it takes open sets to open sets, that is another beautiful property of this map, okay. So the moral of the story is that you not only recover the cylinder as the set of equivalence classes, you actually recover it as this topological space structure on the set of equivalence classes that makes pi a continuous map by the quotient topology, okay. So let me write the following down. Given a small disk d centered at z with pi of z is equal to p on the cylinder, okay, we see that because pi inverse of pi of d is just d and all of its translates, okay, this is a set of all z plus z prime plus n z naught, where z prime is an element of d and n is an integer, okay. Because pi inverse of pi of d is a union, is open, being a union of open sets, okay. So each d plus n z naught is an open set, okay, it is just a translate of d, okay, and the union of all these d plus n z naughts as n varies is precisely what this set is. So in fact I can write this as d plus z times z naught is equal to union n belonging to z d plus n times z naught, and each d plus n times z naught is homeomorphic to d, or even holomorphic, even holomorphically isomorphic, to d, because translation is of course a holomorphic isomorphism, okay. Translation is a holomorphic map and it is injective, and there is an inverse map for translation, okay. So well, so each of these sets is like d and this is a union of these open sets, so it is open, okay. So if you start with a small disk d here, I am going to get its image here as an open set, okay, and this is what is going to help me to give a chart at the point p. Namely, what I do is the following: what is it that I want? I want an open set surrounding the point p, and I want a homeomorphism of that open set with an open subset of the complex plane. So what will I do? I will take this open set pi of d, and the map I will take is pi inverse, and that pi inverse will be not just any pi inverse. I will just take this d itself. I will if I restrict pi to this d, mind you, it is bijective. That is because you see I have made this disk very small, okay. So 2 points in 2 different points in this disk cannot go to, I mean they cannot go to the same point here. If this disk were made large enough so that it extended beyond the boundaries, so for example instead of this disk, suppose I took a huge disk then I will get several points which will go to the same point there. the map will fail to be injective, okay. So that is the reason to choose the disk to be small enough, okay. So that is what is going to help me to give a complex coordinate at this point. So let me do this. We take the pair pi of d comma pi restricted to d inverse as a chart containing P, okay. So what I have finally been able to do is, for every point here I have been able to give you a chart, okay, and I can do this for every point because my point was arbitrary. The only thing that remains to say that this is a Riemann surface is to say that all these charts are compatible, okay. That is the only condition we will have to check, and once we check that, then this collection of charts is going to give you a Riemann surface structure. And of course when we talk about that Riemann surface structure, we of course think of the we also keep in mind the maximal chart which contains this chart, okay. So let me write that down. So we get a collection of charts as above, as P varies that covers your cylinder, okay. Now to say that this collection of charts is an atlas, I will have to just verify the compatibility condition. So let me do that. That is also pretty easy. We can even do it diagrammatically. Of course all these things can be written down a little bit more formally, but nevertheless it's this it's not very difficult to write things down more formally, okay.
Whatever way I cut the cylinder, there will be some boundary points. For that boundary points, how do you give this correspondence?
You mean a neighborhood?
Neighborhood.
No, there is no problem. If the point you select was a point on the dotted line, okay, then you are going to get two representatives for that point, okay. And so here well the point is you are going to get a point, an inverse image will look like Z prime if you want to call it, and you know what you will get is all of its translates, you will get all these points. And if you take a disk like neighborhood, small enough disk like neighborhood surrounding this, then again the image of that small enough disk like neighborhood in for example on this strip you will get so let me rub this off and just put a very small cross here, let me rub this off. So the inverse image of that neighborhood I mean the under this map is going to be, well, you are going to find a piece here, so let me call this as P prime here. So I am going to get a piece here and I am going to get another piece here, but then when you glue it you are going to get, if my point is P prime, I am still going, these two things are going to glue, I am going to still get a nice disk, okay. So in this way you are actually covering every point, even the boundary points, okay. So it will work even if you had chosen a point on the dotted line where you have cut it, okay. And of course here I have put in some arbitrariness because you know the way I pasted this disk on the complex plane, well I could have even kept it vertical or I could have kept it horizontal, but just to give a general case I have put it at an angle and I have drawn the axis arbitrarily so that I get a vector. The only restriction, the way I have done it, is that this vector has to have length equal to the length of the unit circle, nothing more, okay. And even that restriction you can remove, okay. If you remove that restriction and you take any z0 which is non-zero, you are going to get a cylinder anyway. The only thing is that it is not going to be the circle, the perpendicular section of the cylinder is going to be a circle, its radius is not going to be 1, it is going to be something else, but nevertheless it is the same as a cylinder up to a scaling, okay. So it is the same surface, so on that also you will still get a Riemann surface structure, okay. So it is easy to verify that the charts are compatible so that we do get a Riemann surface, we do get an atlas and a Riemann surface structure on the cylinder. Okay, so let me do that a little bit in a diagrammatic way. So you see, so here is my situation, so here is my cylinder, so here is my cylinder, okay, and well I have a point, let me call this as P1, and it is surrounded by a small disk like neighborhood T1. Let me draw it a little bigger so that it is easier to label these things. So here is my point P1 and it is surrounded by disk like neighborhood pi of D1, okay, the way I have done it. So it means that what I've done is, well, here is my complex plane, okay, I have chosen a point Z1, okay, which is being mapped by this map is just the map pi, and this is a cylinder which is identified with the set of equivalence classes, okay. This Z1 is going to go to P1, so P1 is pi of Z1, okay, and of course this pi of D1 is just the image of a disk D1, small enough disk D1 which is surrounding Z1, okay, and then what is this compatibility? I will have to say that whenever two charts intersect, then I will have to say that the transition function is holomorphic, okay. So take another such chart, so that is going to be centered at some other point P2, and this is going to be just pi of D2, where, well, P2 is going to be the image of a point Z2 here, okay. So P2 will be pi of Z2, and D2 is going to be again a small enough disk centered at Z2, right. And what I will have to say is that I will have to say that the transition functions are holomorphic. So what is it that I do? Well, let me write down the transition function. So I have, so the transition function from here to here is, what is this function? This is, well, if you want, let me call it as phi1. Phi1 is just pi restricted to D1 and inverse. That is a transition function, right, because that is the way we have defined it, okay. Always a chart consists of a pair u comma phi, where u is an open set and phi from u to an open subset of the complex plane is a homeomorphism. So my open set is pi d, it is open because I have already proved why it is open because of the quotient topology, and pi restricted to d is a homeomorphism, okay. So pi d inverse is also a homeomorphism, so it is a pi restricted to d inverse is a homeomorphism from pi d to d. So pi restricted to d1 inverse is, if I call it as phi1, it is a homeomorphism from d1 pi d1 to d1. Similarly I will get another homeomorphism like this. This homeomorphism is going to be just phi2, if I want to call it as phi2, it is pi restricted to d2 inverse, right. And what is the condition that I will have to verify? Take this intersection, which is pi d1 intersection pi d2, and this will correspond to, well, a piece of the disk here, okay, and it will also correspond to a piece of the disk here, okay, and I will have to say that the transition function, which is the transition function is now going to go from here to here, which is go by phi2 inverse and then follow it up by phi1. This is my so called G12, my transition function, and I will have to say that this is I will have to say that this is just a holomorphic map. Well, if you complete the picture properly, you can see that if I take all the translates of d1, which will be the inverse image of pi d1 under pi, and if I look at all the translates of d2, in fact what will happen is that I will get, there will be a translate of this d2 which will essentially be like this, okay, and then this d2, this intersection comes from a translate of d1 which will look like this, okay, and these two will be translates of each other, and this translation will be translation by the vector, this will be the vector z0, okay. So what you will get here will be some d2 plus some m times z0, that is what this disk will be, and what you will get, so this is my d1, and let me write it properly, and this is my d2, okay, and this disk will be d1 plus some m prime z0, okay, because you see, if you think about it, these two disks, you go back to this picture, these two disks side by side are going to give you two disks here, and then when I take the inverse image, I am going to get a pair of disks along with their intersections, and they are all translates, okay. So it is actually going to look like this, the only thing is that you see I have to translate this to get this image, and therefore literally my z0 should be in this direction if this image is correct, okay. So the moral of the story is that this G12 is nothing but translation by, you can write that down, what will happen is that you see this disk is d1 plus m prime z0, if I translate it by minus m prime z0 I should get d1, okay, and this disk if I translate it by m z0 I should get this d2 plus m z0. So what it will tell you is that this m is equal to minus m prime, okay, you will get m equal to minus of m prime and G12 to be the map that sends omega to omega if you want plus mz0. This G12 will just be a translation by an integer multiple of z0. You will see that d2 will go to d2 plus mz0, okay, and d1 will go to d1 plus mz0, but m is minus m prime, so it will go, d1 will go to d1 plus d1 plus m prime z0 will go to d1 plus m prime z0 minus m prime z0, so I will get back d1, okay. So you will see that G12 is just translation by a suitable integer multiple of z0, and this is certainly a holomorphic map, it is just a translation, okay. So the moral of the story is if you write it down, you will see that this is just the translation function is just translation by a multiple of integer multiple of z0, okay, and that is holomorphic. So that gives you the compatibility condition between any two charts, okay. You will have to, of course I am assuming that these disks are very small, okay, and then this is true, okay, you can convince yourself, you can write it down. So having done this, we have been able to give a Riemann surface structure on the cylinder, right. Now there is one more aspect of this that one can look at, and that is the so called group theoretic interpretation of this, which I will try to now explain, okay. So let me give you also a group theoretic interpretation. And this interpretation is important because what is going to happen is that the whole idea is that as we will see that we will prove that all Riemann surfaces can be gotten from well known Riemann surfaces like the plane or the Riemann sphere or the unit disk by going modulo a group of automorphisms, okay. So the idea is you can get every Riemann surface as a quotient by a group of automorphisms, and this philosophy in general is called the uniformization theorem, the general uniformization theorem, and this is the technique which allows you to translate questions on Riemann surface to questions on the complex plane or something as simple as the unit disk or this Riemann sphere. Okay, so let me give you this group theoretic interpretation. So what we do is that we first recall that the automorphisms of the complex plane, set of holomorphic automorphisms of the complex plane, that is given by the set of maps of the form z going to a z plus b, where a is not 0, and of course a and b are complex numbers. Okay, so these are all the possible holomorphic automorphisms of the complex plane. Okay, I think you would have proved this in a first course in complex analysis, but if you have not, you can still do it. Well, these are in particular they are Moebius transformations. Okay, now what I am going to do is that I fixed this vector z0 and I was looking at translations by z0, or rather translations by integer multiples of z0. So what I am going to do is instead of looking at z0, I look at the translation by z0. Okay, and mind you, translation by z0 is also an element here, a translation is an element here, namely I take a equal to 1, then it becomes translation by b. Okay, so what I do is that I define this group z times z0. Okay, if I want, rather let me put t z0. Okay, which is what this is, set of all maps z going to ez plus n z0, where n is an integer. Okay, of course mind you, again z0 is not 0 and t z0 is this map, and well, this map will then be n times t z0, and you can check that this is also equal to translation by, of course it is equal to translation of n times z, translation by n times z0. Okay, if t sub lambda denotes translation by lambda. Okay, so here is my group, and you can see that this is isomorphic to the group of integers under addition. After all, two translations, when you so here you see this is a group under composition. Okay, in fact all these holomorphic automorphisms, that itself is a group, and the operation is composition. Take any two holomorphic automorphisms, compose them, you get another holomorphic automorphisms, another holomorphic automorphism. And but the only problem is that that's a, and of course any element here, a holomorphic automorphism here has an inverse. The inverse of a holomorphic automorphism is also a holomorphic automorphism, and you can also write that inverse down explicitly using this formula. Okay, and you will see that the inverse is again a map of this type. Okay, so it's actually a group under composition of mappings, and here how do two elements combine? They combine by composition. So in particular, if I take two translations, they combine by composition. Okay, and that corresponds to adding integers. You see, that's because you see, if I take a complex number z and first apply t by t z0, okay, or let's forget z0, let me put z1. Okay, then all I'll get is I'll get z plus z1. Then if I apply tz2, I'm going to get ez plus z1 plus z2, and you can see that this composition is just t z1 plus z2. It is t z1 z2 composition t z1. First apply t z1, then apply t z2. You get this, and you can see that since I am getting z1 plus z2, it's a commutative group. Okay, so these whether I apply first tz1 and then tz2, or whether I first apply tz2 and then tz1, it's going to give me a commutative group. And in fact you can get this isomorphism by sending the t n z0 to n. So this T nz not going to n, it will be an isomorphism of groups, namely it will preserve the addition here, and the addition here will correspond to addition of integers. So the moral of the story is I am looking at the translations as a group, a subgroup of automorphisms of the complex plane, okay. And you know, whenever a group acts on a set, we can talk about the orbits of the group, okay. The orbits of the group are just given any point of the set, you look at all those points that you get by applying elements of the group, but that in this case just translates to the following: it's you take any point and you just take translates of the point by integer multiples of z0, okay. And therefore the orbit of a point z is just going to be just the equivalence class of the point z. So this tells you that you can think of the quotient, the set of equivalence classes, that is C mod tilde, as the complex plane modulo this group, okay. So you see the cylinder which has been identified with the set of equivalence classes is also just the complex plane modulo this group z t z, okay. It's quotient by a group, okay. And well, if you take this point of view, then it explains that this is also you know, isomorphic to C mod z if you want, because after all z times t z0 can be identified with z by this map, okay. And so what it tells you is that your cylinder is C mod z, basically it's C mod z, complex numbers mod z, okay. And if you really look at it in a very natural way, this should have a group structure. After all, it's a group by a subgroup, right. If you think of Z as sitting inside C as a subgroup, then this is a group, okay. And that should make you expect that there is going to be some group structure on this on the cylinder, and there is, because after all it's S1 cross R, okay. You take an element of S1, both of them are groups. R is a group under addition, S1 is a group under multiplication, and this is just a product group, and therefore this group structure actually is natural to expect. So all I am trying to tell you is that your group structure also comes into the picture if you think of it as a quotient of C by a group of automorphisms, okay. And this viewpoint is going to be extremely important in the lectures that follow, okay. So I will stop here.